Hello, good afternoon, and welcome to Future Tech. My name is Johnny, and today I will talk to you about Microsoft Q# and Azure Quantum. So, let's get down to business. So, first of all, again, my name is Johnny Hooyberghs. I work for a consultancy firm in Belgium, and my main goal is doing backend .NET development. As a consultant and a little bit of architecture. I am a Microsoft MVP in the developer technologies. And if you have any questions after this session, you can always contact me at my Twitter page and on my professional email address, johnny.hooyberghs@involvedit.be. Everything that I'm talking about today will be on my GitHub page, also some code, so you can always take a look at that if you want to dig a little bit deeper. But because today we only have half an hour, but there's so much more that I can tell you, so please have a look at my GitHub page. So let's get started. You to solve it using your computer. He knew that I was doing some Turbo Pascal as a hobby at home, so he thought he would challenge me. So the Knight's Tour is actually a problem where on a chessboard you can have your knight jump around using the horse jump, and you are actually able to visit each square of the board only once and visit all of them. So the teacher told me, write a computer program that just tries to jump around until it can actually find a route that will jump around the entire board, and on the right hand side you can see an example solution that a computer should be able to find. So I thought, this is very easy. There's only 64 squares, so it should be peanuts for a computer to actually solve. So I started developing. Then when I thought I was finished, I ran my application. It ran for a couple of minutes without reaching a result. I thought I made a mistake. I tried again a second time, I tried again a third time. I kept trying, but the computer never found a solution. It ran for multiple hours. It ran overnight. I thought I was just a stupid little boy. I went outside and played with my friends, and I basically abandoned the problem. It was only later that I learned that this kind of problem is actually an exponential problem, which is even for a classical computer very difficult to solve. Because if you make the wrong choices always along the way, you're going to be trying a long time. And again, it looks stupid. It's only 64 squares, but if your computer makes the wrong decisions all the time, it will run for hundreds of years without actually finding a solution, which is mind-blowing, but it is actually true. And there's many more of these kinds of problems that are actually that cannot be solved by classical computers, and that's the reason why we need something different. And hopefully quantum computers can help us resolve those kinds of problems. So what are quantum computers? They are basically based upon concepts from quantum mechanics, and the theory of quantum mechanics is already 100 years old, so we have a lot of knowledge about that. So quantum computers use superposition and entanglement and some other things, but superposition and entanglement are the two most important ones, which are borrowed from quantum mechanics. We don't have time today to go into much detail about this, but in the bottom you can see on the left hand side an image representing the spin of an electron, so a very tiny particle, an electron, that can have a spin up or a spin down, but it can also be in superposition of spin up and down. A lot of people say at the same time, spin up and spin down at the same time, but that's not entirely correct. It's some kind of probability function between up and down. And then on the right hand side you can see entangled qubits, or at least entangled electrons. They are in superposition of spin up and spin down, and two of these particles are entangled together, which means that they influence each other. When we take a measurement, because for superposition, a superposition will collapse into its discrete values upon measurement. So when we look at it, when we take a picture, or when it comes into contact with reality, basically, then it will make a decision based on that probability function. But when two qubits or two electrons are entangled, if we only measure one, the other one will automatically also make a decision the exact same moment in time. Very spooky. We actually don't really know how that works. We only know that it works. So very cool stuff that we can use hopefully with quantum computers. But again, why? Well, there's already a large range of problems that we try to solve with this. For example, security. Today we have devised our own security that is just too hard to crack by classical computers, and it works on a very easy level. Let's say you have a very large number. And that large number is a solution of multiplying two large prime numbers together. Well, this is what public-private key encryption is based on. It's a little bit more difficult than that, but the basic idea is that we have two very large prime numbers, we multiply them together, and the resulting number is even larger. Now, the two separate prime numbers are your private key, and if you multiply them together, you have your public key. And that's how it works. When you give somebody the public key, he will never be able to get back to the original two prime numbers, because you cannot write a computer algorithm on a classical computer that is able to factorize that large number back into its original prime factors. Well, you are able to write an algorithm. You can just brute force and try to multiply all prime numbers together, but a classical computer will take thousands of years to reach a solution, and that's the reason why the security works. But of course, there's other problems like drug development, for example, where we want to do the opposite. We have a very complex problem. We didn't create that problem. We have that problem, and we want to find a solution for that. So when you look inside of your body is made out of millions and billions of tiny particles, atoms, which have electrons and even smaller things. And basically, when we have a disease, some kind of disease, something is wrong inside of our body on a molecular level, on a very tiny level. So we want to introduce an external drug into our system and hopefully help resolve that problem. But how do we know that that drug will actually work? Well, we need some kind of simulation. And that's basically the reason why today there's only two options. There's trying to combine the processing power of all classical computers together to help us simulate what a drug can do to our system, because the problem is just there's so many things going on inside of your body. It's an exponential problem. We cannot simulate our entire system when a drug is being applied. So we try to combine all of the processing power in the world to only help us a very, very small portion. And the other thing that we can do is do animal testing. We can test drugs on animals to see what happens to a living organism, basically. And if it immediately dies, we know, oh, we don't want to use that on humans, unfortunately, because yeah, it's also not fun to kill animals to do something like that. So hopefully when we have quantum computing that has different kinds of properties, we will be able to solve these kinds of problems, because now we can simulate something that is actually quantum by nature. And because drugs introduced to our body is quantum by nature, the drug is quantum by nature. So when we have more knowledge on how quantum works and we can actually use that in computing, then of course we would be a lot closer to resolving our issues with that. A final thing is machine learning, for example. It's basically the same idea. It's an exponential problem, because when we have large quantities of data, multiple variables, and we want to learn something from that, and we want to do that fast, like fast feedback, and there's again, in real life, we have lots of data coming into our eyes, our ears, our taste, our smell, and we take decisions based on that very quickly, because that's how our mind works. Our mind is, again, quantum by nature. It can very quickly make decisions based on the data it gets. But on classical computing hardware, it's still very difficult, because it's an exponential problem, just like the night store problem from earlier in the presentation. And just like with drug development, our mind is quantum by nature. If we understand more about quantum and we can think in the same way, hopefully we can create computers that will work in the same way, and it will be easier to work with these kind of exponential problems. But of course, the most important question of them all is, can a quantum computer run something like Crysis? It looks like a joke, but the story that I want to tell with this is there is going to be a very specific use case for quantum computers, and we will still use classical computers in the future. Classical computers can be for whatever we do today, and running games and things like that, and we will hopefully use quantum computers for very specific purposes. If we have a very difficult exponential problem we need to solve, we will try to solve that part of the problem with a quantum computer, and then we will again revert back to classical hardware to execute the rest of our applications or program or algorithms. So it's actually going to be a combination of we using classical hardware and quantum hardware to solve our problems. Running a computer game on a quantum computer with the model we already have today is in theory possible, because a quantum computer is very compatible with a classical computer because they both work on binary logic, but it just doesn't really make any sense. It would be too expensive, and we have classical hardware that can run Crysis just fine, so we should just continue like that. If you compare classical computers with quantum computers we're thinking about today, they are very similar, like I told you. On a classical hardware, we have bits like zeros and one, and we can combine those bits together to represent all kinds of data. On a quantum computer, we're going to do the same thing, but we're going to use a slightly different notation. This is again a 0 and a 1 bit or qubit or quantum bit, but we use the Dirac notation to specifically tell our readers that we are talking quantum. So this is just the same 0 and 1 as on a classical computer, but now we can use that in quantum formulas, quantum algorithms, stuff like that. And again, the same thing, we can combine those states to actually represent all kinds of data, but we still use that Dirac notation. By the way, Dirac is named after a physicist called Paul Dirac, who invented this kind of notation. But things becoming interesting when we talk about qubits. They cannot only be 0 and 1, they can also be in a superposition of 0 and 1. And then we need to use some mathematics to actually represent that state, that more complex state. And because zeros and ones are very easy for us to think about in the top of our heads, or from the top of our heads, but when we think about superposition, that's a little bit more complicated. That's why we have an expression like this that says we have two probabilities, some kind of alpha probability for it being 0 and some kind of beta probability for it being 1. And then we make things a little bit more complicated because, of course, that's how mathematicians work. When they have a problem that they cannot solve, they just invent some new mathematics in order to express that problem. And that's also the reason why we need complex numbers. So we have complex numbers instead of real numbers to represent these alpha and beta values, unfortunately. But again, this gives us all the tools to represent what we want to do with quantum. So I'm not going to dig very deep into this. Just know that the mathematics is not very hard if you really look into it. And the fun thing about quantum computing is that it's a real use case. It's like a physical use case that you can almost touch, and that makes it a little bit easier to dig into all of these mathematics, because now you have a goal to work towards too. I remember from school I didn't really like mathematics because it was too abstract, but with this you really have something concrete where you can use it for. When we basically want to use mathematics to represent a superposition state, it looks like this. It's 1 over square root of 2, because some kind of expression tells us that this is how you need to represent that, but this is a perfect 50-50 superposition. But again, we won't go into much detail right now. The only thing that I can tell you is that this superposition, this is something that we really need to solve our exponential problems. There is functions that can help us, like a quantum Fourier transform. When we have multiple probabilities, we can actually try to change those probabilities to our benefit, hopefully to make the probability of our solution being higher than the probabilities of the things that are not our solution. I know it sounds very abstract, but that's the whole idea what quantum computing is all about. We want to fiddle around with that superposition state. We want to change that superposition state to our benefit so that our solution will become much easier to find. And again, there's a lot of mathematics involved, but this is another way of representing the state of a single qubit, for example. This is a Bloch sphere. It's a three-dimensional sphere with the x, y, and z axis. And we can actually represent the state of a qubit as a vector in this three-dimensional sphere. Basically, when you have a vector that points straight up the z-axis, it's in 0 state. So it's just the binary 0 state. And when that vector points down the z-axis, it's in 1 state. So that's the two opposites, 1 and 0. But when that vector is anywhere else inside of that sphere, it's in some kind of superposition. And this is where we can play around with those probabilities, because it's very easy to understand. On the right hand side, you can see a vector that points somewhere in the upper half of the sphere. And it's very easy to comprehend that now the probabilities of collapsing to 0, so the vector pointing straight up, it's actually closer than pointing down, because the vector is closer to 0 than it is to 1. So the probability is higher for going to 0 to 1. So we can actually change the orientation of that vector by using quantum hardware to actually change the superposition state of these physical elements that represent the qubit. And it's not going to be a transistor. It's going to be some other thing that has the property of being in some kind of superposition, and we can change that superposition by using all kinds of things. There's different kinds of quantum computers. Today we are experimenting with lasers to change states. We are experimenting with microwaves to change states of electrons and spins. So yeah, still a lot of investigation going on and experimentation going on, but that's the basic idea. Again, when you have some time, please look into stuff like trigonometry, because that can really help you to calculate these probabilities based on angles of vectors. It's all mathematics, but it's all high school level mathematics. It's really not too hard, so you should be fine. But of course, if you really want to dig deep, you need to work a little bit with this stuff. But the power of quantum computing, where does it come from? Well, I told you already, if you have one single qubit, it has these two probability values, alpha and beta. But if you add one qubit to that system and you now have a total of 2 qubits, it will actually, and those are in superposition, I'm sorry, then they will have 4 probabilities, because now you, when they are in perfect superposition, you have a 25% probability of it collapsing to 0, 0, 0, 1, 1, 0, and 1, 1. So now you have these 4 values. And this is where the power of quantum computing comes from. When you have a very large problem scale, you can represent each solution of that problem with one binary state. And when it's a large number of these variables or states, you just need to change the probabilities so that the only solution has the highest probability. So you just need to change those probabilities. And again, if you look at this, for 2 qubits you have 4 of these probabilities, but with 3 qubits you already have 8. And with each qubit you add to that system, you double the amount of probabilities, or double the amount of states that you can represent. And this is again where that power of quantum computing comes from. So just if you look at a classical computer, it has, let's say you have a CPU, let's say, that has 1 billion transistors. If you want to double the amount of processing power, you need to add another billion transistors. So you need to double the amount of transistors, so you double the cost. With a quantum computer, the only thing you need to do is only add 1 qubit. So if you already have 100 qubits, in order to double the amount of processing power, you only need to add a single qubit to that system. And now you have double the amount of processing power. Today, it's not really the cheap option. Quantum computers today are in the very early beginnings. It's very expensive to create a physical quantum computer today. But in the future, hopefully, we will find new materials to use as qubits or to represent qubits, and hopefully it will be cheaper and much easier to have a stable quantum computer by then, and then just adding 1 qubit can just double the amount of processing power. The level where we are today is just circuits and gates, basically, and so we are trying to change these probabilities by rotating vectors around in a Bloch sphere, or doing stuff like entanglement. So we put qubits through gates. That's how it works. Again, I'm not going to go into detail in much theory. I will show you some Q-sharp later on. But we can also draw circuits, just like we can do in just classical binary logic. We put qubits through gates and we do measurements, and based on that we can create circuits like this circuit for entanglement. If you have 2 qubits, the only thing you need to do to entangle them together is put 1 qubit through an Hadamard gate, putting it in superposition, and doing a controlled NOT operation on those 2 qubits to entangle them together. And now when you do a measurement, we don't have 4 probabilities, and 1, 0, 0, 0, 1, 1, 0, 1, 1. No, they are entangled, so both are going to be 1 or both are going to be 0, but not something else. So again, we have two probabilities. Qubits are entangled. This is another example of a circuit called teleportation. So this is actually 3-qubit circuit. On top we have some kind of a message qubit, and we can teleport the complex state of that message qubit to another qubit by running it through this circuit. I'm not going to go into detail, but if you look at my GitHub page, this is implemented using Q#, and you can try to figure it out from my GitHub page. So before we go to Azure Quantum, let's very quickly take a look into Q#. So Microsoft actually created a programming language to do quantum development before they actually had a physical quantum computer, because their idea was that developers should already try to learn quantum today by using tools that they are used to, Visual Studio Code or Visual Studio, to just learn what's out there, and then in the future, when quantum computers actually become a thing, we already know a little bit about them. So that's very cool. Also, this is a quantum program that can actually run on my classical hardware by using a simulated environment. So I'm not going to be able to create very difficult quantum algorithms, but I can learn by doing the easy stuff. And so this is an operation called say hello, but I'm going to do a little bit more. I can, for example, allocate a new qubit. I can put that qubit through an Hadamard gate to put it in superposition. I can have a binary result by measuring that qubit. So it was in superposition, 50-50% chance. I'm measuring it, so it will collapse to either 0 or 1. And then I will do message with some string interpolation to write this binary value to the console. And then I can use .NET to simulate this program by just calling .NET run. And as you already see in the bottom, sometimes it will return 0 and sometimes it will return 1. So this is a very easy Q# program, and this can help you to learn about quantum by creating much more complicated algorithms. As long as you're using less than about 30 qubits, you will be able to run it if you have about 64 gigs of memory. About 30 qubits will use about 64 gigs of memory. So if I go back to the presentation, Q# as a language is already a couple of years old, but today there is something called Azure Quantum, and it's still in preview. But the idea of Azure Quantum is that you can actually use physical quantum hardware in the cloud. So you don't have to buy one and put one in your home. You can use the one that is available through Azure Quantum. And you can use it for multiple reasons. There's quantum optimization if you have very specific optimization problems that need solving. You can do quantum machine learning. You can do quantum simulation if you need larger hardware. For example, on my local system, I can only run about 30 qubits because I have 64 gigs of memory. But on cloud hardware, you can run or simulate multiple more qubits than 30, because there you can have more memory if you want to pay that. But you also have access to physical quantum hardware, and Microsoft is actually doing research for their own quantum hardware. They are using the topological approach. That's one way of doing quantum computers, but Microsoft is not yet ready with that. But there's also external vendors that Microsoft is partnered with that can help you to run your Q# applications on real quantum hardware. And an example is IonQ or Honeywell, which are two separate companies, and they are using ion-trapped quantum computers. Ion-trapped quantum computers use ions, and they will use laser beams to change the states of qubits. Then there's also QCI, which is another vendor. Those are using superconducting quantum computers, and they're using electrons and microwaves to change qubit states. Now, Microsoft already created the Q# and the Quantum Development Kit a couple of years ago for us to already learn about this quantum stuff. But today, because we have Azure Quantum, they actually are doing the same thing as what we do with .NET already. So Q# is a high-level language where we can create quantum algorithms with. But of course, we need to translate that into machine code. But the machine code is different for different kinds of hardware vendors. IonQ, Honeywell, QCI, Microsoft, it's all different kinds of quantum hardware that will work in different ways. So Microsoft introduced the quantum intermediate representation, which is what your Q# will be compiled down to. So it's kind of a lower level language that is compatible with the universal quantum computer. So it's basically putting qubits through gates in circuits. That's what it all comes down to. And then that quantum intermediate representation language can be sent to the drivers from these specific hardware vendors, and they can translate that down into the machine code that is compatible with their specific machine. So again, this will help us developers to only think on a very high level abstract concepts, and then the hardware vendors, they will translate that down into their machines so it can actually run on their machine. So it's very interesting that we don't really need to write machine code, although it still looks a little bit like machine code today. But in the future of Q#, there will be layers on top of those circuits, and we can basically call functions and operations instead of just putting qubits through gates. That's the idea. So Q# will evolve into a much higher level programming language that can still run on these quantum hardware. So let's very quickly show you what that looks like in Azure. So in Azure, it is in preview, so it should be available to everyone. When you create a new resource, you can just find Azure Quantum, and this will create an Azure Quantum workspace. I'm not going to create one because I already created one, which is this one. But basically you have a list of providers, and this list of providers you can add or remove providers. So for example, I've chosen to work with IonQ and their physical quantum hardware, and then the Microsoft Quantum Inspired Optimization, which is a software version of quantum. So this is not real quantum hardware, but it can help you solve your problems for quantum inspired optimization if you have optimization problems. But you can very easily add providers, like I can add Honeywell, or I can add 1QCloud, and in the future when new vendors come into the Azure Quantum space, you can also add them and use them based on the kinds of problems you have. So how do you actually run stuff on Azure Quantum? Well, I can go back to Q#, and I've actually created an application like this. So if you do Q# create new project, you can write a console application to do simulation on your local machine, but you can also create applications targeting very specific quantum hardware. The reason why you can specify quantum hardware is because there are some differences, and I will show you later. But this is, for example, an entanglement circuit. So I'm actually allocating 2 qubits, and instead of putting a qubit into perfect superposition using the Hadamard gate, I'm going to use a rotation around the y-axis. So again, this is the block sphere, and I'm doing a rotation around the y-axis, and I'm going to do a rotation of 2 pi over 3 radians. So it's not in degrees, it's in radians, again, mathematics. But 2 pi over 3 radians is about 120 degrees, if I'm not mistaken. And then I'm going to use the controlled NOT gate to entangle those 2 qubits together. And then I'm going to return the measurement of those 2 qubits. So if I do .NET run for a simulation, they will either be 00 or 11. But the probabilities are a little bit different now because I'm not doing a 50-50%, I'm actually doing a 75-25%. So basically I can run this multiple times, and I should see that if I do it an infinite amount of times, there's going to be a 25%, 75% probability here. But I can actually also run this on Azure Quantum. So I can do Azure using the Azure CLI for PowerShell. So Azure Quantum Execute, and I'm going to use the IonQ simulator target. So IonQ has both the physical hardware and the simulated software for you to run your applications. I'm going to use the simulator because it's going to be a lot faster, because lots of people are actually testing the actual physical quantum hardware, so that can actually take hours until it's my turn in the queue, basically. So when I use the simulator, things will go a little bit faster. So let's see what happens. I still have to be a little bit patient. It's running. And the difference here with running it locally is that when you run it locally, it will only run once. But if you run it on quantum hardware, by default, I think it will run 100 or 400 times, and it will automatically show you these probabilities. So it says that item 1 is 0 and item 2 is 0, or item 1 is 1 and item 2 is 1. So again, qubits are entangled, and it's going to be 0, 0 in 25% of the times, and it's going to be 1, 1 in 75% of the times. And if I run this using the actual IonQ quantum processing unit and I press enter, it will do the same thing, but it will take a couple of hours until it's my turn in the queue, and then it will show me the exact same result. Again, when you have real difficult things that you need to do with qubits that you cannot run on your local machine. In the future, hopefully, when pushing it through to Azure Quantum, it can actually solve for many more qubits. And with that, I'm at the end of my presentation. So again, we didn't really have a lot of time, but there's so much more for you to learn. Read about quantum. If you are into the Microsoft world and community, there's lots of documentation, lots of stuff you can learn with and learn from. There's many Q-Sharp examples on my GitHub page. I've created a very specific page for this conference. So my PowerPoint deck is also part of that repository. So please take a look. And if you have any questions, don't hesitate to ask them. And again, enjoy the rest of your presentation, and thank you for attending.